Chapter 10, the Internet. The Internet. And here are the objectives. After reading this chapter, you should be able to discuss the responsibilities of the IP protocol and how it can be used to create a connection between networks, to identify both IPv4 and v6, discuss the responsibilities of TCP IP, identify relationship between TCP IP, ICM, UDP, ARP, DHCP, NAT, and tunneling protocols. Describe the responsibility of the domain name system, DNS, and how it converts URL into dotted decimal IP address. Describe the major internet application and services. Discuss the basic advantages of the www. Recognize the internet is constantly evolving and that IPv6 and Internet 2 demonstrates that evolution. So this chapter 10, about the internet, and we just read the objectives. Introduction. Originally, the internet TCP IP was used in the ARPANET. Of course, if you read a different reference from a different background, they might tell you different things. And in '83, the Department of Defense broke the ARPANET into smaller networks, the ARPANET and the MILNET, which was for military use only, although the MILNET remained essentially the same over time. The ARPANET was eventually phased and replaced with a newer technology. During this period, the National Science Foundation funded the creation of the new high-speed cross-country network backbone called the NSFnet. The backbone is the main telecommunication line through the network connecting the major router sites across the country. See the old NSF, whatever. So this is just historic stuff. Supporting the internet are a host of protocols. Two of the most common protocols are the Internet Protocol and the Transmission Control Protocol, TCP. These protocols are themselves supported by host and secondary protocols, which include the Internet Control Message Protocol, ICMP, User Datagram Protocol, UDP, Address Recognition Protocol, ARP, Dynamic Host Configuration Protocol, DHCP, and Network Address Translation, or NAT, Network Address Translation, all right? Many people think the internet is merely the application that allows a person to browse the web page and click the links, but the internet actually comprises a wide range of services. One of the first and still popular services offered on the internet is email. Other services made possible by the internet includes IM, instant messaging, file transfer using FTP protocol, remote desktop and remote administration, internet telephony, voice over IP, lists serves, and streaming audio and video. The impact of www and other internet functions on the business community has been monumental. By the late 90s, an entirely new field of business had come into existence. It's called e-commerce or electronic commerce. Now you can buy practically anything on the internet. Entertainment, medicine, groceries, real estate, mortgage, and automobiles are just few of the products available online through e-commerce. And of course, this comes with its challenges and security concerns, all right? Internet protocols, hierarchy of layers as created by Department of Defense, just 4 layers, all right? Internet protocol, IP. IP datagram is essentially another name for data packet. So it's just a packet, all right? They call it datagram. And this figure shows a progression of packet from one network to another. So local workstation, and it goes from data application layer, then transport layer that adds transport header, then network layer that adds an IP header, transport header, and data, then the MAC interface layer that has the media access control header, IP header, transport header, the data itself, and the MAC trailer. Now we have a trailer, and then we send it over the network, and it goes backward, and it goes on, right? When a router has the IP datagram, it makes several decisions affecting the datagram's future. In particular, the router might perform the following functions: make routing decisions based on the address portion of the IP datagram, fragment the datagram to smaller datagrams if the next network to be traversed has a smaller maximum packet size than the current size of the packet, decide that the current datagram has been hopping around the network for too long and delete the datagram. IPv4 datagram format. Format of IPv4 datagram. 4 bits for the version, 4 bits for the here, 8 bits here, total length 16, identification, the flag, the fragment offset, time to live, protocol, header checksum, source IP address, destination IP address, IP options, padding, then the data that has a variable length. And this is the biggest thing, in fact. Format of IPv4 datagram. So this is the data packet and this is the headers, all right? All right. IP fragmentation. And here are some details. IPv4 addresses. As already noted, IPv4 addresses are 32-bit in length. 8 and 8, 16, and 8 and 8, another 16. The total is 32 bits. For example, a valid IPv4 address might look like the following, just like this. All right. Five basic forms of 32-bit IP address: Class A, Class B, Class C, Class D, Class E. Class A, 128 addresses because it uses 7 bits. Class B, it uses 14 bits, so it provides 16,000 plus addresses. Class C, over 2 million addresses because it uses 21. The Class D multicast addresses, the old ones reserved addresses. And in the Class A, we have host address, host ID, 24-bit, and in Class B, yeah, just the classes. A, B, C, D, E. A, B, C, D, E. 5 types, 5 classes. We are talking about the IPv4, the 32-bit IP address. We have 5 basic forms, okay? As mentioned earlier, each IP address consists of 3 parts. Identifier field. a net ID, which indicates a particular network. Host ID indicates a particular host or computer. So identifier fields are the beginning bit pattern, just a beginning bit pattern. It can be 1, 2, 3, or 4-bit identifier field. A net ID indicates the particular network, and a host ID indicates a particular host or computer on that network. All right, that's the IP address. Multicasting is the capability of a network server to transmit a data stream to more than one host at a time. Multicast, sent to a group. So unicast sending from one to one, multicast from one to group, broadcast from one to everybody. And subnet masking. The basic idea behind subnet masking is to take the host ID portion of an IP address and further divide it into subnet ID and host ID. Using this technique, an internet service provider and a company can take a large number of host IDs and break them into subnets. Each subnet can then support smaller number of hosts. Makes it easier. Subnets. IPv6, Internet Protocol version 6. All right. So the demands are the packets, the number of users, and the packets transmitted. So IPv6 was created to fulfill the needs. Several notable differences exist between v6 and v4. The first concern addressing. As you learned, IPv4 uses 32-bit addresses, or v4, 4 bytes. With explosive growth of internet, concern arose that the current system would run out of IP addresses in no so distant future. They were right. We did run out of IPv4 addresses in 2011. Consequently, IPv6 calls for addresses to be 128 bits long. 128 bits long. It's not a 32-bit. 4 times the addressing ability, but it's way more. 128-bit address gives a virtually unlimited addresses. The number is really high. With the internet will be able to assign 1 million IP addresses every picosecond for the non-age of the universe. Needless to say, IPv6, we will never run out of addresses. Significant changes were also made to the IP header between version 4 and version 6. As you may recall from figure 10.4, the IP header in version 4 contains 14 fields. In IPv6, the IP header contains 8 fields only, less fields, plus the payload data and optional extension headers. As shown on 10.6, let's scroll down and see the difference. 10.6. The field in IPv6 header, less, it's 8, and extension headers. So it's really different. The version, the priority, the flow label, the payload length, the next header, the hop limit, the source address, destination address, payload, and all right. So IPv6 has a better support for options using extension headers, better security, with 2 extension headers devoted entirely to security. So the extension headers is for security, all right? More choices in type of service. Last improvement to IP relates to the quality of service, which is an important part of modern networks. Quality of service. It's a very useful tool. If a user can specify a particular level of service and the network can support that level, IPv6 should deliver better quality of service than IPv4. IPv6 addresses. IPv6 addresses are 128 bits in length. This provides virtually unlimited source of IP addresses. The size alone makes it challenging simply to reference them. For example, they are usually written in hexadecimal form, where each 4 bits is quantity is replaced by hexadecimal digits from, okay. So every 2 hexadecimal, every 2 is a byte. This is 1 byte. This is the second, 3, 4. All right. 4 bytes, 6, 8 bytes, and then this is another 8 bytes. So 8, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8. All right. So that's 8 by 8. 64. Looks like it's more than that. All right. And now it should be 128. Like 264s, okay? And here's the address for the IPv6. And the TCP protocol, the transmission control protocol. We talked about the IP protocol. Usually they say TCP IP, okay? Perhaps one of the most common examples of transport layer is the TCP, is the other half of the protocol, the TCP protocol. The primary function of the transport control protocol is to turn an unreliable network that's connectionless into a reliable network that's connection, that's free from loss and duplicated. Thus, TCP IP essentially fills some holes created by the IP. But how can a transport layer protocol make an unreliable network to reliable? To make a network more reliable, TCP performs the following 6 functions. So the TCP functions are these 6 functions. Create a connection, release a connection, implement flow control, establish multiplexing, perform error recovery, establish priority. And each one is explained in details in this paper. If we keep going, TCP datagram format. What's the format for the packet, for the datagram of the TCP? The field of the TCP header. We see the TCP header contains fields shown in this figure. Let's examine only those fields that assist TCP in performing the 6 functions listed earlier. The first 2 TCP header files, source and destination, contains the addresses of the application programs at the 2 ends of the transport connection. These port addresses are used in creating and terminating connections. The port number, so we have the port number here. And we have the sequence number and the closure number and the HLN and the reserve flags window, checksum, urgent pointer, padding, yeah. These port addresses are used in creating and terminating connection. The port number can also be used to multiplex multiple transport connections over a single IP connection. It is important to note the difference between IP address and port number. The IP address identifies a device connected to the internet, while the port number identifies an application on that device. Working together, the two create what is called a socket. This is important in programming, opening a socket, closing a socket, just using a socket, okay? A precise identification of a particular application on a particular device. This is called a socket. And there's a socket IO, all right? What if your company has one server that handles both email and FTP connection? The server would have one IP address but two different port numbers, one for the email application and one for the FTP application. Now let us add the fact that this server is more likely on a local area network and thus have a network interface card which with a unique 48-bit NIC address, right? Network interface card, which is the MAC address. Now we have three addresses: the NIC address used by the local area network card to find a particular device. The IP address is used to move data packets through the internet. The port number is used to identify the particular application on the device. The sequence number field contains 32-bit, the sequence number field. So we are done with that port number part. Now we're going to talk about the sequence number. We are talking about the header of the TCP packets or datagrams, all right? The sequence number contains a 32-bit value that counts bytes and indicates the packet's data position within the connection. For example, if you are in the middle of a long connection in which thousands of bytes are being transferred, the sequence number tells you the exact position of this packet within the sequence. So it's the packet number among the packet stream for this connection. This field can be used to reassemble the pieces at the receiving workstation. So it's a sequence of the packet. The window field contains a sliding window value that provides flow control between the two endpoints. If one end of the connection wants other end of the connection to stop sending data, the window field can be set to 0. Checksum field is the next field. It provides an arithmetic checksum of the header, and the data field follows the header. The urgent pointer is used to inform the receiving workstation that this packet of data contains an urgent data. Urgent means the priority. Like its counterpart, TCP IP is fairly streamlined protocol. Its primary goal is to create an error-free end-to-end connection across one or more networks. TCP and IP do have their shortcomings. However, these have typically led to problems such as security weakness, quality of service issues, and congestion control. Thus, both of these protocols will need to continue to evolve. But even though their basic components should remain in existence for a long time, the Internet Control Message Protocol and it's used by routers of nodes perform this error reporting of the Internet Protocol. All ICMP or Internet Control Message Protocol messages contains at least 3 fields: a type, a code, and first 8 bytes of the IP datagram that cause the ICMP message to be generated. So the Internet Control Message Protocol, as an IP datagram moves through the network, a number of things can go wrong. As datagram near its intended destination, a router may determine that the destination host is unreachable. The destination port is unknown, or the destination network is unknown. If a datagram has been on the network too long, its time to live value expires. The datagram will be discarded. Also, there could be something wrong with the entire IP header of the datagram. In each of these cases, it would be nice if the router or some other device would send an error message back to the source workstation informing the user or the application software of a problem. The Internet Protocol was not designed to return error messages, so something else is going to have to perform this operation. So the ICMP, the Internet Control Message Protocol, generates these messages. UDP. The TCP IP is the protocol used by most network and network applications to create an error-free end-to-end network connection. TCP is a connection-oriented in that a connection via a port must be established before any data can be transferred. If you do not want to establish a connection with the receiver but simply want to send a packet of data, in this case, User Datagram Protocol or UDP is the protocol to use. UDP is no-frill transport protocol that does not establish a connection, does not establish connections, does not attempt to keep data packets in sequence, does not watch for datagrams that have existed too long. Its header contains only 4 fields: the source, the port, the destination, the port, the link, the checksum. And it is used by a small number of network services such as DNS that do not need to establish a connection before sending data. So DNS use UDP, and UDP is really efficient and fast. Multi-protocol label switching. This is for more details, right? And it's very nice and useful. And here we go. Multi-protocol label switching is a technique that enables a router to switch data from one path onto another path. To make this possible, one or more label header files information are encapsulated onto the front of the IP packet. All right. First label, second label, yeah. Address Resolution Protocol, or ARP. The Address Resolution Protocol is another small important protocol that used to support TCP IP network. The Address Resolution Protocol takes an IP address in the IP datagram, translated into the appropriate medium access control layer for delivery on a local area network. As mentioned earlier, every workstation has its own connection to the internet that assigned an IP address. This IP address is what the packet uses to find its way to its intended destination. There is one problem, however, when a workstation is, for example, an Ethernet or CSMA CD local area network. Recall that piece of data that traverses on a CSMA CD LAN is called a frame. This frame consists of a number of fields of information, none of which is an IP address. If the frame is supposed to go to a particular workstation with a unique IP address, but the frame does not contain an IP address, how does the frame know where to go? ARP provides an answer to this question after an IP datagram enters CSMA CD LAN through a router, and before its IP header is stripped off to leave only the frame. The ARP broadcasts a message to the LAN asking which workstation belongs to this IP address. The workstation that recognizes the IP address sends a message back saying, "Yes, that's my IP address. and here is my 48-bit CSMA address. Please forward that IP packet to me via this address. The 48-bit NIC address is stored in the buffer, and just in case it will be needed again in the near future, so it will be cached. Dhcp assigns IP addresses. When a company installs a number of computer workstations and intends to give them all internet access, it must assign each of them an IP address. This IP address, as we have learned, allows workstation to send and receive information over the internet. The basic method are used to assign IP address workstation: static assignment and dynamic assignment. It's either dynamic or static IP addresses. The dynamic is done through the Dhcp protocol. With a static assignment, somebody sits down at each machine and, using the network operating system, installs the IP address. What happens if the workstation statically assigned? Someone has to make sure the IP address assigned to that machine is removed. Then the most popular protocol that handles dynamic assignment for the IP addresses is called the Dhcp, and there should be a Dhcp server. All right. Users who connect to the internet from home often use Dhcp without knowing it. Rather than assigning an IP address every potential user, an internet service provider's Dhcp server assigns an IP address during the session creation. The computer uses the temporary IP address until the user logs off, at which time the address is placed back into the pool and ready for the next user. And NAT, Network Address Translation. Another protocol that used to assign IP addresses is Network Address Translation. More precisely, NAT lets a router represent an entire local area network to the internet as a single IP address. So the router shows like a single IP address. When a user workstation on a company local area network sends a packet to the internet, the NAT replaces the IP address of the user's workstation with the corporate global IP address. So it's like a global IP. In fact, all packets that leaves the corporate contains this global IP address. Thus, the only IP address that anyone sees outside of the corporate network is the one global IP address. Of all packets from all workstations leave the corporate network with the same IP address, how do responses that come back from the internet get directed to the proper machine? The NATed software maintains a cache listing all IP packets that were sent out and who sent the packet. When the response comes back, the NAT checks the cache to see who originally sent the request. When NAT finds the match, it removes the global IP address, reinserts the user's workstation, and places the packet on the corporate network. What happens if a packet arrives at the corporate NAT software and there is no cache entry with the matching outgoing request? In this case, the packet is destroyed. All right. Tunneling protocol and VPN connections or VPN networks. Tunneling protocols to open a tunnel, virtual private network to open a virtual. One of the more serious problems with the internet is lack of security.